Okay, good morning. Today is June 22nd, and this is the John Chappell Natural Philosophy Society. I am your host, Franklin Hu, and we meet here every Saturday on Fuse. And you can find us on social media, on Facebook, and on YouTube. And if you'd like to help us out, please drop us a line at hqnaturalphilosophy.org. And these are our rules of conduct. And next week, we will be having our conference. So probably instead of having a science chat next week, I'd probably just invite you to tune in to the live broadcasts. So on Saturday, I believe I'll probably be speaking from 9 to 11 a.m. Pacific Standard Time. So, but I would invite you to tune in on those live broadcasts. And we'll be having Dr. Gerald Pollack. All right, so the discussion here today, I think I just pick a topic. And I'd like to talk about the magnetic field, but rather than me blabbing on about my thoughts on the subject, I want to get your thoughts. So Dennis has started us out asking about the magnetic field, and I guess
hang on a second, Franklin. For the tuning into the conference next week, do we just do the same thing that we do to connect here to this chat, or what?
No, you would have to go. I'll probably, when I send out the announcement, there'll be a link to YouTube. So
okay.
If you go to YouTube and you search for John Chappell Natural Philosophy Society, there will likely be a live link. And when we are broadcasting live, you'll be able to click on the link and view the live presentations. And that will actually be going on all week. Well, since starting next Wednesday, you can go there. You can go to the John Chappell Natural Philosophy Society, which is naturalphilosophy.org, and click on there. Click on the information for the conference, and on the right-hand bar, there's like a schedule. So you can see who we have scheduled starting from Wednesday through Saturday. And you can probably tune in almost any time, Pacific Standard Time, between about 9 till 4 p.m., I believe. We have speakers doing 60-minute presentations pretty much the whole day long. So I would invite you to check that out. And like I said, I will probably, in lieu of the announcement for the science chat, I'll send out information on how you can join the live stream for our conference this year.
Okay, thanks.
Okay, so I want to talk a bit about the magnetic field. It seems like the magnetic field, though, is a very mysterious thing. The mainstream itself, if it's being honest, would probably say they really don't understand the basics of what makes the magnetic field work, or at least that there's no general consensus. And even among the dissident science crowd, I don't find too many people trying to put forth an explanation about how that works either. But so Dennis, I believe you started off the discussion here asking about, I believe you asked whether the magnetic field itself is able to describe the effects that we see, or that you need curl or something like that.
Yeah, the B field is what you ordinarily think of as the magnetic field. The H field and the B field are closely connected. But as far as the B field is concerned, the curl of the magnetic vector potential A is equal to B. So the question then arises, is this relation one-to-one and reversible? No, it's not. The curl throws away information. Consequently, the question then comes up, is the B field all you'll ever have to know, Or, on the contrary, you have to know about the A field in certain important situations, that information that the B field has lost through taking of the curl, which is a vector operator. Well, I have a paper which I talked about before in my talk on why quantum mechanics works even though it's crazy. And this paper is talks about the A field explaining the Crane-Monstein magnetic effect, which is if you have a cylindrical permanent magnet and you rotate it about its axis of symmetry at a constant angular velocity, then the magnetic field either becomes stronger or weaker depending on which direction you rotated it. So how do we explain this? If you think of electrons as toroids of charge, then if they were all lined up as they basically are, the free electrons anyway are all lined up in a permanent magnet, then it would make sense that if you rotate one way, you would increase the rotation, the net rotation of the electrons, which would increase the magnetic field, and rotate in the other direction, you decrease. And this paper is available on academia.edu and also on researchgate.com, two websites, research websites. And I get pretty good results and seem to be able to explain this, but I point out in the paper that if you try to use the B field, you don't get the right answer. You have a singularity and you can't really proceed. So it seems that the big problem with why people don't understand the magnetic field nowadays is that they don't realize that the A field is what you should look at, the magnetic vector potential field, and in general, and not the B field, although the B field is adequate for many important problems.
So I'm not quite sure if I understand what the problem is. So if you have the Lorentz Force Law is what is typically used to describe the effect of the magnetic field.
Yeah.
And that uses what? The B field?
Yes.
And so the B field is defined by the lines that say iron filings produce around a permanent magnet. You see those?
There is a slight complication. There's an H field and another one which I can't remember at the moment. And but in open space, where you're away from magnetic materials, the B field and the H field are the same. And so now you might say, well, yes, but you're talking about a permanent magnet. That's not away from magnetic field, from magnetic material. No, but one can solve the problem of the equation between H and B, and I can't think of the other letter, but there's another letter, M. That's right. M is the permanent magnet effect. But I analyzed in my paper, in terms of the B field, and I mentioned the H and the M fields too, and explain how all that works out. But basically, the B field is the one that's important. Oh, here we go. Yeah. Well, this is the Lorentz law of force. All right. Incidentally, I do not go with the Lorentz law of force, although a lot of people do, including Bill Lucas, I understand. I go with J.P. Wesley's Scientific Physics, 2002, chapters 4 and 5 talk about how Lorentz Force Law is just a special case of a more general law.
Well, I'm all confused about all the various symbols used to represent the magnetic field. So there is B, and then there's something called H, and now you're telling me there's something called A.
Yes. There's A. The A is what gives B. Curl A is B. The curl is a vector operator which takes you from a vector field to a vector field. But it's not one-to-one. It throws away information.
So you're saying that this curl is more fundamental than the observed magnetic field.
So the curl is the magnetic field, but the curl of A is B. But A contains more information than B because the curl operator throws away information. It's not one-to-one.
And for those of us who are not mathematicians like I am, so what does the curl equation do? What does it physically mean?
It means that if you think of, for example, a current flowing in a circle, circular wire, a current flowing in it, that you could say it curls around the center of the circle.
Oh, I can understand that, but I can't see how that can form an operator. Like multiplication is an operator.
You really need to look at the vector definition of curl. Can you bring that up? Oh, you got del cross. You had. Can you bring up the curl operator? Yeah.
Curl, mathematics.
Yeah, here. The vector calculus, stop. In the vector calculus, the curl is a vector operator that describes the infinitesimal rotation of a vector field in three-dimensional Euclidean space. Every point in the field, the curl of that point is represented by a vector. The attributes of this vector, length and direction, characterize the rotation at that point.
So I'm not quite sure I understand. I mean, I can understand if you have a field of vectors and those vectors are constantly rotating about some axis.
No. The vectors don't rotate. Vectors are just to have length and direction.
Well, they can definitely rotate, right?
Well,
I'm trying to understand.
But if you take a snapshot, the curl operator looks just at the snapshot in an instant of time.
It does, but looking at this definition, it looks like, first of all, you have a field of vectors,
which means that you have a vector at every point, and as you go from point to point, the vectors are there's a continuity condition, which says that they don't, they're all. If you take a very small circle, a sphere about a point in Euclidean space, if it's small enough, the vectors corresponding to the points inside the sphere are approximately the same, a continuity condition. In fact, it's different. It has to be differential.
Well, what I'm seeing here is that the curl is just a measure of the rate of rotation.
Well,
that's what it says. The direction of the curl is the axis of rotation as determined by the right-hand rule, and the magnitude of the curl is the magnitude of rotation.
Yeah, but the curl operator does not differentiate with respect to time.
that doesn't matter. It's the magnitude of rotation. It would be expressed in you know, like angles per second or something like that.
I'm not kind of at a loss here to explain this. You know,
Although none of this is really explaining the fundamental question I'm trying to get at, which is, you know, how does the magnetic field work? One of the most fundamental
you have
things.
to find out what characterizes the magnetic effects before you can answer that question. In other words, if you're looking at B, but B doesn't tell the whole story, you have what's called a hidden variable.
Well, still, if there's a hidden variable, that's still a empirical formula approach to the problem, and not explaining why is it when I mean, the simplest case would be you have a wire, it's carrying current, and then you shoot an electron at that wire.
Yes.
And you find that the electron changes direction.
That's right.
Now, the only things that we have in this system is we have a physical wire, we have electrons moving in that wire, presumably, although some people would even dispute that. And then we have another electron heading at basically perpendicular to the direction of the current, and it causes the electron to deflect in basically the direction that the current is flowing. If you apply Lorentz Force Law and all that other stuff, it does end up being that the electron is deflected, so it begins to, and if you let it go, it would actually flow in the same direction as the flow. I mean, in some ways, that seems you can understand it as I don't know, it's like the electrons are creating like a river of something, and then when some object approaches that river, it just flows down with the same kind of stream that it's creating. Because some people think that a magnetic field is actually physically a flow of something. And if you take a magnet, they kind of think that there is actually some kind of fluid which is constantly being rotated around the magnet. Is one possible thing. Like, I've done some experiments. Let me see if I can find my experiments here with the magnetic field. And one of them was to see what happens when you stick a magnet on an old CRT screen. So you've probably seen that, but it's kind of hard to see what it actually does. And it does create something which kind of looks like a vortex. So let's see if I can find my video on that. So we're going to go to my YouTube channel here. I'm going to look at all my videos. And I've got like 100 videos. So if you guys ever get bored, you can check out all the crazy stuff I do. Okay, here we go. Here's the video I'm going to show you here. So this is a simple black and white CRT screen, and I just projected a crosshair on the screen. Right? So I've got a very strong super magnet. I'm just going to stick that on the screen, and you can see what happens when you do that.
In the center of the screen, I've projected onto this TV a cross. And
so what do you think is going to happen?
The magnet towards it.
If I put it right in the center, you can see it literally twists that cross.
Like a clockwise direction. And if I flip the magnet around.
And if I flip the magnet around, then it makes it go in the opposite direction.
So it's kind of like you can think of like a tornado or a vortex that's spinning around like this way.
You could see that would kind of be like a vortex, and if you flip the magnet around, that it would cause the flow to go in the other direction.
Spinning the other way, and it twists around the other way. And the other thing is if I put it in the side of the magnet and it's twisting up and down this way.
Now I also put it
pushes
on the side of the magnet, so you can see that it pushes down only one axis.
Put it around the other side.
And you flip it around, and it pushes it up the other way.
So in some ways, it's easy to think of the forces that get generated by the magnet as being similar to like a vortex, which is spin.
So that's just an example of one of the effects that can be demonstrated using magnets.
Yes.
And that's an interesting demonstration because we have all the necessary elements, which is that we have a magnet, and then we have electrons being shot at the magnet, and we can keep track of where the electron beam is going because we've projected it basically onto the screen. So that is the very, very basic thing that we want to explain, which is why that happens. Now, one of the things that this video is showing is that it's kind of consistent with it creating a vortex around the magnet. That's kind of like spinning around the axis is one possible interpretation.
In a straight wire with constant current, the magnetic field lines are circles with center at the wire and plane perpendicular, lying in a plane perpendicular to the wire. And that's somewhat true for magnets like the one you've got in your hand there. But the A field for a long straight wire with a constant current is lines through the wire perpendicular to the wire.
The A field?
Yeah.
The A field you feel is perpendicular to the wire?
Yes. If you have a long straight wire with constant current, and you want to know what the A field lines look like, they're straight lines through the wire perpendicular to the wire.
But still, that really isn't motivating, why should the electron deflect in the field? I mean, I don't care whether it's A or B or H or whatever. There's something that's causing the electron to change direction. So what is that?
What is what?
What causes the electron to change direction?
It's just it's a empirical law. You can argue that, there must be an ether. Newton said, yeah, there has to be an ether, but I have no idea what it is. There has to be an ether, and if you understood the ether, then you'd understand what causes the electrons that you were mentioning to behave as you showed they do. I'm not into ether theory because I feel that, well, there has to be an ether, like Newton was right. The ether will only be discovered when everything else is figured out. In other words, it's going to be the last thing that we figure out before we finish up.
Or maybe it has to be the first thing you have to figure out.
No, I wish that were true, but...
Because all of these things kind of fall into the same category of forces. Gravity falls into that category. Nobody knows how that works, really. Even the electrostatic force between charges, I was trying to discuss that. There's no real consensus on how that works. And then we have magnetism, and there's even probably less consensus on how that thing works. So it's like we are, and the extent to which we don't know how these things works is great. I mean, it's not like we're close, and it's just a matter of time before we figure out what it is. It's like most mainstream physicists will just simply shrug their shoulders and say, we have no idea, right? So this is a field which is ripe for dissidence because This is not anything that the mainstream immediately has any kind of explanation for. They could say you're wrong because it works this way. So see, Michael, you've raised your flag.
Well, I have my own ether theory, and it makes sense of all this on a very basic level, which is that...
So explain, Michael, before you go on and explain about your etheric particles and, how they join together and how they do that, can you just explain to us how you think the magnetic field, why does an electron deflect in a magnetic field? And in your theory, what exactly is the magnetic field? So please try and not repeat yourself, but concentrate on those two questions.
Well, you have to start with the ether because the ether...
Well, we know what your ether is. So
the ether furnishes linear forces which underpin the stability and the orderliness of all the quantum forces. I mean, it's a very simple, a basic concept you have to start with. It's because the ether is perfectly linear. It has the magnetic... it has a vibratory linear mechanism of interaction between elemental units, which are identical, and they act by direct vibratory contact, and they also are elemental, so they are the basic building blocks of all the quantum units.
Yes, so we understand that. That's great. But let's take a wire, you put a current through it. Now, somehow, that changes the space around the wire to have what we possess as a magnetic field. So I'm asking you, in your theory, what is the difference between space which contains a magnetic field and space which does not?
Well, it's a setup that you construct, which could be a wire with poles, or it could be a cosmic situation where you have two poles of a rotating body where you have a lot
I'm not talking about two poles of a rotating body. I'm talking about straight wire. You attach a battery to it, causes a current to flow or something that generates magnetic field. So, or you can answer saying that you don't know what it is. I mean, that is the answer that most everyone will give. So I don't want you to pretend that you have an answer if you don't. But if you do have an answer as to what is different about the space around the current carrying wire, that's what I want to know.
Well, the ether is the basic driving force. The ether exists in the space around the wire and exists in the wire, but it's the setup of the apparatus which accelerates the ether to form etheroidal units, and you get a cascade of etheroidal units, and you get the wave.
Well, once again, that's not explaining magnetism.
Well, in the ether model that I have, it's the ether vibrates, and that means that there has to be a tiny empty space between the vibrating units. And when you form when you have a setup where there's an increased amount of electromagnetic energy, then you have greater alignment and entrainment of the elemental units, which forms larger etheroidal units. And this eliminates the space, because when they connect up, the space where they vibrate is no longer there, because now they're connected up, and that vibratory space is not there. And so you have the situation where you have magnetic attraction, for example, vibratory patterns of in the ether, which may be more similar vibratory pattern of the ether, which control
I'm not getting any answer from you to my questions. I mean, first of all, answer yes or no. Do you believe?
I can't give you a simple one sentence answer, because it goes back. It has to devolve back to the ether as being the underlying driving force of the whole thing.
But you haven't given me any motivation as to why, say, for example, the Lorentz Force Law is correct. Can you in any way explain or derive or, explicitly explain what is going on with this cross product. Because one of the most craziest things about the magnetic field is this whole cross product thing, this QV cross B. And what does the cross part mean? Well, the cross part means you have to, take your hand and point your thumb and your first finger and your middle finger in 3 different directions, and you have to align the direction of the current in one of your fingers, the magnetic field in the other finger, and then the force results as being at a right angle to both of those things. So there's nothing actually going in the direction of the force, and that's pretty crazy. How that cross product thing works. And it's like, I want to know whether you have the answer to what caused it. And every single time I ask you that question, you're just giving me these generic things about your ether theory. At some point, it has to get down to a mechanical point where you can say that, well, you have a current running down the wire. That wire is doing something to your etheroid particles, which causes them to exert forces on other charges which are approaching that wire.
Well, the wire and all that, that's all artificial apparatus setups. That depends on the setup, but it's not, that doesn't really give you the basic forces that are underlying the
no, it doesn't depend on the setup. I mean, the setup I gave you is very simple. Current carrying wire, charge approaching wire, causes charge to deflect in the direction of the flow of the current. That's what we observe.
Well, the ether units are linear, and they connect up, and that's what underlies the stability, for example, of an atom, which has charge. It has an electronic charge and it has a nuclear charge, and they have, how do they connect up? The only way they connect up is through the linear the intervening ether matrix, which contains the linear connections, which enables the quantum units to be in a stable, orderly pattern.
And once again, I keep on explaining to you that none of that is explaining is answering the question. I mean, every single time I ask you a question, you basically say the same thing, right? But none of that is really motivating me to say what is going on in the space around a current carrying wire.
At last I managed to join this. I don't know if you can hear me.
We can hear you.
Yeah, I couldn't get through the protocol for months. And now I have a tiny little face at the top talking. I don't know who he is. And I see my own face. So I'll keep quiet, shall I?
All right. Well, welcome to join us. But we were discussing with Michael and Tesky, who has, we've like I say, you tend to just repeat yourself no matter what question is asked to you. And I know you're trying to relate the basics of your theory, but as near as I can tell, none of that will deflect a charge around a current carrying wire.
Well, the ether exists in the space around the wire, but it's just not as intense as in the wire because of the apparatus and the setup, which is artificial and doesn't really well suited to my basic idea of the ether. We can't detect the ether, so we can't define the fine details of how the ether works. The contribution of etheroidal transition from etheroidal to subquantum and all that. It's just not possible because
then let me just
all we get to go by is the quantum observations, and it just doesn't answer the.
Let me just ask you this simple question. I want a yes or no answer. So, can you explain what is the physical manifestation of a magnetic field? Yes or no? Don't explain it. I just want to know whether you think you can explain that. Yes or no?
Well, I think it's an energy that.
No, I didn't ask you to explain it. First of all, I want to know yes or no. Do you know what the physical manifestation is of a magnetic field in the space around the wire? Yes or no?
Well, I'd say yes, basically.
Okay, good. So you say yes. Okay, so what is the difference in the physical manifestation around the wire then?
It's an energy process in which the ether around around an electric current is reacting to the basic setup, which is you have two poles which are at an opposite electrical charge, and it's the same thing that's going on in the wire, only it's in space, and the ether is in both places. The ether is in the reaction and the energy which causes the ether units to align and entrain and form electrons is more intense in the wire, but it's basically the same thing in the space around the wire.
And once again, I don't know why that would cause an electron to deflect around the space around the current carrying wire.
Well, I think that's probably an apparatus-related effect. I can't. I'm just an ether theorist. I'm not a quantum physicist, so I really I'm at a loss to go to the into detail on the quantum observations.
Well, that's okay. I mean, if your theory gets that far, then that's fine. I just trying to figure out exactly where your theory goes. So your theory may not exactly get to that level where it's showing at a fine-grained detail why the electron just happens to curve in the presence of all that, right? Although as an etherist, I would think that all of these phenomenon occur within the ether, so that probably all of these effects are caused by the ether, not unless you think that it's something unrelated, which it could be. It could be that you have an ether and it has nothing to do with magnetism. That's possible. Okay, so I see Ian has raised his flag. So Ian, why don't you go ahead?
Thank you, Franklin. Okay, I'm going to attempt to answer your question, maybe not thoroughly with regard to precisely what's happening physically, but before I do that, just a couple of questions on what was said at the beginning of the conference, which you may wish to revert to later. First, as regards the A and B fields, well, one must remember basically that the vector potential is just a means of an alternative means of mathematically determining a value of circulation over a curve, over a closed line, if you like, and the magnetic field intensity is basically doing the same with regard to flux through a surface. So it's basically, this is the Stokes business. So you're actually converting, evaluating the evaluation to a vector potential. Now, if it's maintained, as has been done earlier, that the vector potential is more fundamental, one might then pose the question as to whether, similarly, the scalar potential would be more fundamental than the electric field strength. So that's just something that came out of the earlier discussion. Now, as regards this whole business, I'm interested, as you probably know, in analogs, and I've been struck by the analog of, say, something like circular motion in dynamics, where you obviously have what we might call an absolute frame. And if there is motion relative to that absolute frame, you seem to get apparent forces like centrifugal forces and Coriolis forces and so on. And there's a big argument as how real they are. But you can sort of you can postulate those forces. They occur as soon as you're moving relative to this absolute frame, and that occurs in circular motion. And hey presto, this cross product which you were querying a moment ago enters into the whole fray, because you have the cross product of the radius vector and the velocity, and concerned with the well, it's the other way around. It's the angular velocity and cross product of angular velocity and radius vector giving the actual velocity. So there's an analog between the this right-handed business in regard to the Lorentz law, and therefore it's a relativistic motion. You have a sort of electrons, if you like, moving in a wire, which can be considered a sort of a quasi-absolute frame, perhaps in the ether, if you wish to look at it that way. And if you have motion relative to that, well, then you're getting a sort of an apparent force coming in, which is like the Coriolis force, for example, or the centrifugal force. And we call that the magnetic force. Now, I maintain that that's fundamental, and I maintain that the mainstream are putting out that this is concerned merely with special relativity, that special relativity predicts this magnetic field and classical physics doesn't. Well, I maintain that it's any relative motion between the velocity of the electrons in the wire and, in this case, maybe a static observer in the ether. And the mathematical laws are quite analogous to that appearing in circular motion in an absolute frame. Now, you did ask further. You prompted Michael then further, and you might do the same to me. You might say, well, what's happening physically? And that's a much more difficult question. I mean, I'm just saying that one can quantify what happens because it's a relative motion. What's happening physically is a bit more difficult, and I might say, well, it's something to do with the alignment of the electrons or something like that. But so if you pose to me the same questions as you posed to Michael, I would probably say, well, physically, I don't really know what happens. I have some idea, and I can give that to you. Mathematically, I sort of do know what's happening because I can very precisely calculate what's happening. But to put a physical model on that, I have to sort of just bring in some ideas by trial and error, and I think it's probably something to do with alignment.
Well, it may be. I mean, what are your new things on what's going on?
What's going on? Yeah. Well, like, I mean, do you ask the same?
You've got a wire, you've got current, and then you've got an electron approaching. Now, just like in the video that I showed with the TV screen, you can see the deflection happening. The deflection is kind of consistent with there being like some kind of vortex around the permanent magnet kind of thing. But, what do you think causes that?
Well, I think it's really the same as causes a motion, say a centrifugal moving away from the center of rotation of a spinning object because of the inertia of the object, and this is moving relative to the center of rotation. Now you might say to me, but what actually is causing that? Why are the molecules flying out away from the center? Well, I mean, one can look at that physically, but it's a force that you have to postulate in order to describe what's actually happening with the laws of dynamics, because you have a system which is moving relative to an absolute frame, and therefore you have an omega cross R term, which is basically coming into the equation, and similarly you have a V cross B term, which is coming into the electrodynamic term.
Well, it would seem that one of the main characteristics that we can measure about the magnetic field is that A, it has a direction. So if we were to think that the magnetic field lines are the same things that show up when we sprinkle iron filings around the magnet, that vector direction is the direction of the lines, so that's definitely one characteristic. So it has a vector and it also has a magnitude. So we feel that the magnetic field lines closer to the magnet are stronger than the ones which are far away. So the magnetic field, for one thing, seems to be a vector field. It has direction and it has magnitude. So it didn't necessarily have to have those two things. It could just, I don't know, have a magnitude but no direction. But it definitely has, you can draw an arrow that represents the direction and strength of the magnetic field. So whatever the magnetic field is, it has to be able to represent at least that, right? So there's got to be something different about the space that has the magnetic field versus the space that, you know, doesn't have the magnetic field. And you could do that by just turning off the current on the wire, and suddenly, if you had like a compass or something in the area, you'd see the compass would just return back to its normal alignment. Where versus when you turn the wire on, the compass just strongly aligns to the same direction as the wire, right?
To me, that would be the same as, say, stopping this disc rotating. If you suddenly stop it rotating, you would diminish, you would get rid of the centrifugal forces immediately. Now, that's the same.
I don't know that the magnetic field has anything to do with the centrifugal force. Maybe, do you think it does?
Well, when you put anything to do with it, I'm talking about an analog. Now, I perhaps don't go quite as far as somebody like David Tome does. I think in some of his papers, he would say they're basically the same thing. I don't do that, but I think they basically follow the same laws, the same structures.
Now, I also know that you mentioned the relativity argument. Now, if there's any explanation for magnetism out there that is even mildly accepted by the mainstream, it's this relativity argument that magnetism is a relativistic effect. That essentially, I think it goes something along the lines that the moving charge is moving faster in time than the stationary charges of something, and that causes basically a charge differential, and that's what is causing the magnetic field, which seems like a lot of hooey to me. But they have videos about it, so probably if you go ask, you know, how do magnets work on YouTube, that video will show up, and they try to explain how it works that way. But in that way, fundamentally, then they're saying that the deflection is caused by this asymmetric charge distribution that happens due to moving charges. But, you know, fundamentally, the force would be electrostatic. So I don't know if I believe that, but so I see, Bill, you've had your flag up. So why don't you go ahead? So, you know, I was just reviewing your book here, and I noticed that, do you explain how the magnetic field works? I don't see a section in your book on it.
Actually, you all are taking a too simple approach to the problem. The first thing you need to look at is the experiments of William Hooper. And in the chat, I put a reference so you can go online and get the paper where he, first paper where he put out the measurements he made on the electric, the magnetic field, and the gravitational fields. And there are 3 kinds of electric fields and 3 kinds of magnetic fields, and there are 13 properties that he measured of each of these 6 fields, and all of them are different. And so you're not taking into account any of that definition, any of that information. So I want to point that out. This on the
well, I don't know that we need to, because we were just trying to explain the simple observation that you have current carrying wire, you have charge approaching current carrying wire, it fails to go straight. So if you're saying that, I mean, that may be very interesting about all the empirical measurements of how the magnetic field works, and there's 13 kind of properties you can find. And that's all great, but none of it is telling us why the electron deflects, right?
But you can't explain what's going on in terms of a physical model unless your model can explain all 13 characteristics of electric and magnetic fields. You are only looking at one.
You can explain.
You're
Well,
looking at one. There's 13 characteristics. You're oversimplifying the problem. The second thing is we're not following the instructions that our earlier scientists gave us, like Isaac Newton, and he said what you're supposed to do is to measure empirically all these properties, these things, and write down empirical laws, then solve them simultaneously to find the most general solution from which you can explain all these phenomena. We're not doing that. And one of the empirical laws is that del dot B is equal to 0, assuming there are no magnetic monopoles, but you have magnetic monopoles probably in your house, and you have never noticed them. They're called refrigerator magnets, and they're rectangular in shape, or square in shape, and they're thin. They're brown colored usually. They come from China. Our scientific community refuses to recognize their magnetic monopoles, but if you do experiments on them, you can see that they are.
well, no, I mean, people have done. I mean, that's trivially refuted. If you take a magnetic sheet sensor, which shows the directions of the north-south poles, and you place it upon the back of your standard refrigerator magnet, you'll find that there are north-south stripes on that refrigerator magnet, right? Now, I've explained this to you, Bill.
No, they're all the same. They're all the same. There's no north and south.
No, there is. There's definitely a north-south.
No, I did experiments on it. There's no north and south. There's only either a north or a south. All of the lines are either north or all of them are south.
No, I'm sure I can find a reference on that. If you put a magnetic sheet sensor on the back of a standard magnet, you'll see.
I've done that. And if you put it,
there are stripes.
There's two sides to the magnet. You can put it on either side, and one side has the field, and the other side has nothing. Nothing.
No, that's absolutely not true. You can stick a your refrigerator magnet either way, and it'll still stick, right?
No, if you turn it upside down from the way you normally put it on the refrigerator, it'll just fall. It isn't attracted at all to the refrigerator.
No,
so
that's not true. Let's see if I can find that here. Magnetic field detection sheet. Okay. Yeah, they have these things.
I show those. And you can see that there's no north and south pole, and you can see that only one side of the magnet is magnetic, and the other side has no field at all.
Okay, here's a picture here. Can you see that? Magnetic viewing film showing magnetic poles of a refrigerator magnet.
That's not the kind I showed. Mine don't have those curly parts on the end. There's nothing like that.
Well, you've got the
different material.
Here.
This is not the normal refrigerator magnet.
No, this is the normal refrigerator magnet.
I have hundreds of them. I don't have any like that. Not a single one.
No,
someone had that made just to do their argument that they wanted to do.
No, you can actually feel it. If you take two refrigerator magnets and you stick them together, as you slide them, you can hear bump, 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 bump,
That's
bump.
right. But that is because the magnets are monopole, and that's what causes the clicking. This won't cause clicking.
No, I mean, that is caused by what we would normally understand as the reaction switching between north and south, right? If it was monopole, then it'd be smooth. There'd be no pole, right? But definitely in a refrigerator magnet, you stick them together, you get it definitely wants to only stick in certain areas, which is consistent with this picture.
Do you have a refrigerator magnet and one of these sheets that shows with the magnetic field? If you do,
yeah, I have a picture of it right here.
You won't see that.
There's a picture.
You'll see the parallel lines, but you won't see the curl around the end.
Well, I mean, that's the point. You see the lines. The lines are showing the line is showing that it's not a monopole.
This is not a monopole in the picture you're showing, but that is not the typical refrigerator magnet. That is a very special magnet that someone made.
No, I don't think so.
Well, I just take your sheet and put it on your refrigerator magnets, and if you do what I do, all you'll see is the straight lines, and they don't make it all the way to the edge. They end before they get there.
Well, I would more believe this website. Because there's no reason for them to.
I believe my own experimental observations. I don't believe other people's pictures because I don't know everything about what they've got. But I have hundreds of types of refrigerator magnets, and none are like that you see on the screen there. None.
Well, every refrigerator magnet, I mean, like I said, the evidence to me, myself, is when I put two of these sheets together, it definitely sticks in some places and wants to repel in others. And it does so in a stripy fashion. So, plus, I believe if you go look to how they manufacture refrigerator magnets, that's how they do it. They induce a striped magnetic field on the sheet, and that's why it generally doesn't look like it has a pole, but because the poles are alternating across the sheet.
Chinese advertise their refrigerator magnets as monopole magnets on the internet, and in scientific articles they do that. You're choosing something that someone has put up for political reasons, not because they're scientific.
Let's see here. How are refrigerator magnets made? Let's see. Well, we have some confirmation that refrigerator magnets only stick on one side. Let's see here.
Yeah. Now, if our picture was correct that you saw, it should stick on both sides, but it doesn't.
Let's see. Now, these refrigerator magnets are the type that are made with permanent magnets. Now, here we have the picture of the magnetic viewing thing again here.
Yeah, I have that same material for investigating, but that magnet, if you were to turn it over on the other side, it would stick to the refrigerator. But the typical refrigerator magnet doesn't do that. It just falls down. It's only magnetic on one side. That's because each of those lines is one particular monopole magnet.
I'm going to get myself a refrigerator magnet. I'll be right back. Okay, let's see here. I got myself some refrigerator magnets here. Okay. So I'm going to stick it on there. Okay, so I can see that it sticks on the proper side. I'm going to flip it around. And indeed, it does not stick on the paper side.
You can take the paper side off, and it still won't stick.
Okay, so now if I tick
this one shown in the picture here would stick both ways.
Now, if I go and I stick both of my refrigerator magnets together like this, now when I pull them apart, they go. They will only stick in very specific spots. Now, if I pull it this way,
Have you measured the
they
distance?
don't seem to care.
Have you measured
But
the distance that you have to move it in order to get it to stop and have a stable situation?
Yeah, so it's about, about maybe an eighth of an inch.
Okay, well now you compare that with what you
can see it
when
you pull this thing apart
with the magnetic film, viewing film.
See, now, to me, that's perfectly consistent with what that magnetic viewing film was showing, which is it's magnetized across like this axis. And so they will only click together because the north will attract the south. And when you move it, then you would have the north facing the north. And so that's why it would only stick in one place. So to me, this is clearly not a monopole. So, if it were a monopole, then it would stick. It would stick smoothly, and this does not. There's definitely some striping going on here, no doubt. Some kind of striping going on here. So,
if you were to take a regular magnets and do the same thing, you wouldn't get that clicking sound as it moves along. You've got to realize you're not seeing the same thing.
That's because these are magnetized in stripes. North, south, north, south, north, south. That's exactly.
But they're made in terms of linear monopole magnets that are put in this material. They don't come. They're only on the surface. They're not on the back side. If you turn that over and move it along, see what you see. What do you see?
Yeah, interestingly enough, you see nothing. So that moves smoothly.
That's right. You can only have that with monopole magnets. You can't have it with dipole magnets. You don't seem to get it.
Well, that is mysterious. I mean, I never noticed that if you took one of these refrigerator magnets and trying to stick it on the other side, that it doesn't work. That's interesting.
Yeah.
But still, it has this, and I would think that, these things are not so thick that the force would be completely eliminated. And you're saying that even if I take the paper off,
yeah,
that it's directly sticking on this.
Take the side that's got the field on it and put a piece of paper on it and see if it won't hold the piece of paper on the refrigerator.
Yeah, and that will work too. I'm sure that if I take a piece of paper and I stick it on here and yeah, it's able to hold on even though this paper is just as thick as the paper on the other side.
Yeah. Okay. The second point I want to make.
But still, none of that motivates as to why the electron deflects in magnetic field. None of it. I mean,
wait a minute.
That's the basic question.
Is one of the 13 properties that William Hooper measured. One of the 13. You've got to explain all 13 properties.
I would be happy to explain even one of them.
So anyway, my work does that. But what I want to point out is if you have the existence of a monopole magnet, then one of the 6 empirical equations of Maxwell, del dot B equals 0, is incorrect. It's del dot B equals something related to the monopole magnet. And that means that the vector potential approach is false. It has been falsified by the data. And so all of the development of electrodynamics in terms of the vector potential A are false. I use the real potential, not the vector potential, the same potential you would use in electrostatic work. And so that is important to know. And you should be able to predict all of the 13 properties. I gave you the paper. They list the properties on the paper. And there are 3 kinds of magnetic fields, not 1, 3. And there are 3 kinds of electric fields. And there is a time-dependent field. There is a field of both electric and magnetic that depends on the cross product of the velocity. And then there is the static field. And each of those fields are different, and they have different properties. Different experiments can show what the properties are, and so we need to see all of those things. And according to the work of Isaac Newton, he said you must take all of your data that you have, your empirical data, in which case, in the case of William Hooper, it's 13 properties of the 6 types of electric and magnetic fields. You need to be able to have all that and then solve all that simultaneously to get a more general theory from which you can now explain all the experiments that produce those empirical laws. And
well, I don't know that even that's necessarily true. I mean, we could take 2, I don't know, arbitrary formulas. You could take the kinetic energy formula, E equals 1/2 mv squared, and then some other arbitrary formula.
That's a classical.
The temperature still formula, P equals nVRT. And you're saying that in order to understand it, you have to be able to solve those simultaneously?
Those don't apply to electrodynamics. Those are classical mechanics.
Yeah, but I mean, fundamentally, the philosophy here don't make any sense.
Well, if you do the electrodynamics correctly, you should be able to define what mass is. Nobody has ever defined what mass is. They all admitted they couldn't. Einstein said he didn't know what mass was. Newton said he didn't know what mass was. And you can also define what charge is. Everybody doesn't know what charge is. But Winston Bostick and his mentor, Arthur Compton, they enabled us to know what charge is. And so you need to look at their experiments that they did with,
well, we're kind of concentrating on the magnetic field
and making solitons. And then you find out that solitons related to charge. And it enables you to define what charge is.
So let's just stick with the magnetic field here. So the main problem I have with this is all just empirical explanation, which is you do your experiment and then you find the equation that fits that, which is great. That's what scientists do. But none of that tells us what the physical mechanism behind the phenomenon is. So, I'm going to ask you the same question.
Take all of the data into account. You're just looking at one piece. There's 6 types of electric-magnetic fields and 13 properties. So how much is that? That's 78 types of experiments you must be able to explain with your explanation to be complete. And you're not doing that. You're only looking at one thing.
Well, we're looking at specific phenomena. So I'm going to ask the same question I've asked to everybody else.
Just one thing, your theory is not necessarily true. It has to explain all of them, or it's still false.
Well, then I'm asking for your explanation.
Well, I just told you. It's Winston Bostick and Arthur Compton. They discovered.
They don't explain it at all.
Yes, they do. You don't know what they're doing. What they do, they explain by experiment that the soliton of the electromagnetic field is the source of all matter, all elementary particles, and that there's no such thing as charge. Charge is just an approximation for the field of a soliton. And you can,
so Bill,
you can show that is true.
I'm going to ask you the same question I've asked everybody, which is, what is physically different about the space around a wire carrying current, which we feel generates a magnetic field, and a wire, space around a wire, which is not carrying current, which we feel does not?
If I use an electron microscope, I can see without any current in the wire that I can see the magnetic fields.
That's not explaining to me what's happening outside the wire. Quite clearly, the magnetic field emanates outside of the whatever's motivating it, which is the current.
You can see it on the surface of the wire without any current in it. You can see the electromagnetic fields of due to the lattice structure of the wire.
And what's happening outside that lattice structure, out in empty space?
There is no such thing as empty space. We don't know any place in the world, in the universe, where you do not have
Nonetheless,
one of the various types, at least one of the various types of electric and magnetic fields. You cannot shield
them. There's a difference between the space when the current is turned on and when the current is turned off. So what is the physical difference? This is the fundamental question of what is the magnetic field composed of? What is different?
The magnetic field is just disturbed when you have a current flowing in the wire.
And disturbed in what way?
Disturbed so that you have a net field that's not canceling out as you get further away from the wire. But if you look inside the wire, you can see what's going on. And that's what we do with electron microscopes. We actually we can look at the wire before the current flows, we can look at it while the current flows, and we can see the change in the lattice structure causing the net field that you see.
So you think that there's some physical change in the actual atomic structure of the wire?
Not the atomic structure, the what do you call it? The crystalline structure. And you will find if you don't have any crystalline structure, you don't have any current.
Well, you can send current through like salt water. I don't think water has any kind of crystalline structure. And that would clearly create magnetic fields, I would think.
Well, you're about to have this fellow speak on water at the meeting next week, right?
Sure.
He'll tell you about this crystalline structure of water.
Well, that only exists on, he says, the very surface. It means basically a surface whenever water is interfacing between some other material. That's his fourth state of water. So I don't think that has anything to do with
No, it goes further than that. I've seen pictures that show it go a lot deeper than that. And but anyway, what you see is he is getting down to the more fundamental part of explaining some of the properties of water. He's not looking to explain magnetic field and electric field particularly, but he is looking at explaining certain properties of water. And we need to, and this is the problem with modern science. You see, the role of logic has been taken out of modern science. You don't falsify theories like relativity theory, special relativity, general relativity. It has those theories, both those theories have between 3 and 5 false assumptions. But in order to preserve those theories, they took the role of logic out. So in what we call the existential philosophy of science, or existential scientific method, and the postmodern scientific method, both do not use logic to falsify a theory. They only use predictions of the theory, not the logic.
Today's topic is still magnetism. So now, now basically when I ask you what magnetism is, you refer to, like Hooper and those guys. But you haven't actually presented any actual explanation from them, I guess. So, I mean, this is kind of a problem.
Well, you should read the paper I referenced there. You can download it and read it it's in the chat. You can download it and read it, and you'll see what he measured, and then you'll see how the experimental data agrees with your approach.
Well, once again, this is all empirical. There's nothing to motivate why the electron actually deflects. They can explain everything about why the electron deflects, and that's trivial because we have engineers and we engineer all kinds of things based on our knowledge about the forces that are generated by magnetic fields. But the controversy here is not that. The controversy here is what is the physical thing that's going on with the electron in space that causes it to change direction, right? So, Bill, do you have an idea? Can you tell us, like the mainstream idea of how magnetism works is like this relativity thing, and it creates some kind of more positive charge in one place and negative charge in the other, and that causes deflection.
Okay.
That's
if
one
you want
possible
a physical explanation.
Yes, we want a
The
physical
universe consists of the electric and magnetic fields. Okay? All matter are solitons in that field. Solitons have very long lived because of the strength of the electromagnetic force. And so when according to William Hooper, the electric and magnetic fields are continuous and have tensile strength. So, two electric and magnetic fields cannot cross without exerting a force on one another due to this tensile strength. The tensile strength goes for as far as large as the universe is. So we have an explanation now for the origin of all elementary particles. We have an explanation for how there can be different forces, what's going to deflect an electron if you put a magnetic field, if you have a beam of electrons like you would have in a TV tube, and you bring a magnet up to it, it's going to deflect that. But it's the interaction of the electric and magnetic fields and the tensile strength of the fields that's causing this to happen. And you don't have action at a distance, you have a continuity, so you can actually see these fields. In fact, the people who were developing electrodynamics, they realized that, and they just made pictures of that. They didn't know about solitons, but they made pictures of the electric and field lines and that sort of thing because they could understand better when they had a picture. And so that's what they did before they even had the proof that these fields do exist. They're continuous and they have tensile strength, and that is what all forces are dependent on. In fact, in my book, I published on the universal force, I show that all the forces in nature, gravity and electrodynamics, are due to electrodynamics and the field strength. And the other forces, the strong interaction force and the weak interaction force, are no longer supported by the nuclear isotope data. We've now measured to 8 significant figures, 3,500 nuclear isotopes, and there is not one piece of data for all 3,500 isotopes in favor of strong interaction force and weak interaction.
Let's get back to the magnetic field. So I believe one of the fundamental tenets that you've got here is that the electric and magnetic fields are, quote unquote, fundamental, right?
Yes.
Now that meaning that they don't exist, they're not composed of anything. So is the electric field different than the magnetic field? Or are those two different fields superimposed on space? How do you see that?
There are 3 types of electric fields and 3 types of magnetic fields, and they are all different properties.
So you're saying there are 6 different fundamental fields then?
Well, the field, it can be manipulated in such a way that you form structures like the regular electric field does not have magnetic properties. But if you make a soliton in the electric field, you now have a source of magnetic property. And then depending upon,
Let's just stick. I mean, one of your fields is like the static magnetic field, right?
yeah,
So that would be the field generated by a non-moving magnet or a non-moving wire, current carrying wire, right?
it's by a soliton. And of course, you realize when you have a wire, you don't just have one thing, a physical wire. When you look at it with a microscope, electron microscope or whatever, you see you've got billions of things in there, and they form structures. And you can see those structures when you do the electron microscope. You can disturb the structure. You can perform experiments in the structure. You can do lots of things. And so when you don't take all that into account, you're oversimplifying the problem.
Well, I think that though simplification is something that science normally uses. I mean, I actually don't buy this thing where you have to explain everything all at once. I don't buy that at all. I think that you need to start with little baby steps. Take the simplest physical situation you can possibly find with the fewest possible variables, where you are pretty sure you know everything that's going on, and you try to come up with a hypothesis to explain that. Now, if
you've got all these experiments by William Hooper, and you're ignoring all of them.
No, everything by William Hooper is all empirical. Everything by William Hooper is empirical, which is, we know how magnetic fields work.
All experiments are empirical.
But that's not what we're looking for here. I mean, I'm looking at this paper now, and it's like, it's all empirical. There's no motivation to what actually causes these effects to happen. He's measured these things. He's written down equations. He's got experiments, and that's all fantastic, but none of it motivates,
right?
Why
Thompson and Vincent Bostic did explain that.
Well, then how did he explain that? That's what the
in
purpose
terms
of
solitons in the field. Soliton is like a standing wave in the field. And if you look at the different approaches that many of us are taking, we have one aspect or another that's part of the picture, but we don't have the complete picture.
But I'm not sure that you even have a picture in your mind as to why these things happen. I mean,
what I did is I took the complete set of the empirical laws of electrodynamics.
And once again, empirical laws.
That was never done by the people like Albert Einstein. They threw away some terms. They didn't use some of the equations, and they made all kinds of assumptions which were in addition to the empirical laws, and so they ended up with an incomplete version of electrodynamics. For instance, special relativity comes out directly from the empirical laws of electrodynamics, directly, with none of the assumptions of relativity theory. But it comes directly out of that. So one sees a lot of things that are going on, and when you follow the logical procedure for making progress. And that was published by Isaac Newton in his book, Mathematical Principles of Natural Philosophy. He was trying to say, if you don't follow these principles, you'll never agree with one another and you'll never find the ultimate solution.
Well, getting back to Meg, I mean, what near as I can tell, because you postulate the existence of the magnetic and electric fields, basically because you postulated that, you don't actually have to explain what actually causes the attraction. Now, I can kind of understand that.
I've never found any place in the universe where there isn't an electric and magnetic field.
I mean, I can kind of understand that, but that may just be a limitation on your postulate. I mean, if I explain to you, if you were to try to explain to me why is it the electron deflects, you'd have to say it's due to the magnetic field, which is completely fundamental.
It's due to the magnetic fields of the solitons and the electric fields of the solitons. Of course, the electron's made of solitons, and the permanent magnet is also made of solitons. And so these soliton fields are what are interacting with one another.
mean, basically your idea is because it's like if you had two magnets and the electron's a magnet and the wire is creating like a magnetic alignment, and the reason why the electron deflects is because it's literally being repelled by the other magnetic effects, which I suppose, you know, you'd have to just understand it that way, right? It's like the electron has a magnetic field. The electrons that are flowing in the wire have a magnetic field, and they're generating it. I mean, I don't know. You could probably do this in a more precise manner, but to show that basically you have a north facing a south, and it's causing the electron to turn direction or something like that.
Also, when you try to explain some of these things, you've also got to worry about the problem. Well, what about all these elementary particles that we have discovered? You know.
Well, no, I think that is a mistake, and I'll have to just stop you right there, because oftentimes when we do these discussions, we're trying to concentrate on one particular aspect, like the electric field or the magnetic field or what gravity is. Then, yeah, people go in and they say, oh, well, you have to explain everything else in the universe. And I'll say, no, that is a needless distraction at this point. I mean, it eventually, I mean, if it's related, I suppose you would have to get into it. But otherwise, I kind of disagree with that philosophy.
Yeah. All the so-called forces in nature are the strong interaction, weak interaction, gravity, and electromagnetic. Gravity has now been derived from the soliton, the base theory of electrodynamics, and it is able to now explain the gravitational force better than any previous theory. Newton's universal law of gravitation, Einstein's general relativity theory. We do not need dark matter and dark energy because we predict all the data that's based on that idea directly from electrodynamics of everything that's made of solitons. And so you see that, and then you take your soliton structures and say, well, how can solitons combine to produce different types of elementary particles? And so you can say, okay, from geometry, we know that these are the stable, reasonably stable structures, and so we now can say what they are. And then, of course, you know, in say elementary particle physics, we say, well, the proton and the neutron and other particles are made of quarks, and the quarks have a certain geometric structure, and we can measure that. But now we're able to predict that from basic electrodynamics, and we are not only able to predict that, but we're able to predict all the known measured properties of these elementary particles, their mass. We can tell you what mass is now. We're able to determine their spin, their net charge, their decay modes, and all that sort of thing can now come out of this. So you see, we're not just dealing with electrodynamics alone. We're now showing that the electrodynamic approach is able to explain more things, including life, and including how you can cure disease electrodynamically, and all kinds of things are coming out of this. And so we can't just say, well, you know, you do your area. That's what the postmodern philosophy of science says. Well, you have a silo here. The chemists are in this silo, the physicists are here, the astronomers are there, the biologists are here. They keep them all separate because they don't want to admit that there is a universal solution, because they have some hidden reasons they don't want to admit it, and they don't allow it to be taught.
But the basic problem here we're trying to discuss here is the mystery of, say, the magnetic field, which I don't think in your theory we're going to get to, because the nature of the force is fundamental. So we're not really going to explain, you know, why the answer for, you know, why does the electron deflect is because of the magnetic field. And it's like, okay, well, That's
The
possible.
electron
But
is made of magnetic fields, and the magnet is made of electromagnetic fields, and there's a tensile strength to the field, and they cannot overlap. They put a force on one another, and so that's what happens. You see a move.
yeah, they put a force on each other, but it's like as a person wanting to know why, it's like, well, why do they put a force on each other? Well, I mean, your
Because
theory,
the
that's fundamental.
electromagnetic field has tensile strength. That's why, and that is what William Hooper proved by his experiments. And it wasn't done in the dark. It was done at University of California at Berkeley, which is a very, active.
But once again, that's all empirical. It doesn't have no motivation behind what actually is going on there physically, or just
if you don't have empirical data, you don't have it. That's it.
Nothing. I mean, all of that's empirical. Empirical is important, but has no explanatory power.
Sure, it explains all these other fields, not just that deflection of the electron by a magnet, but it explains what are all the different forms of matter. It explains, what determines the structure of our solar system and of galaxies and overall structure of the universe.
Yeah, but we know that, like, once again, that's all empirical. Once you have the magnetic field in hand, then you can do all those things. But once you have the electric and the magnetic field in hand, then you can do all those things. But
you see, you don't have 3 types of electric fields and 3 types of magnetic fields. But experimentally, we do.
Well, I may have an argument, but actually, so I want to go on with see who else here might have some comments. I notice we have Ivor Cat here with us. Hi, Ivor. How you doing? Thanks for joining us. So I was wondering, do you have any thoughts, Ivor, on the magnetic field? I don't think this is an area of your concentration about what's going on with the magnetic field. But the floor is open for anyone else who has a comment on the magnetic field. And I have kind of been searching for like a physical explanation for what the magnetic field is and how it works, and what other ideas people have. I was wondering to say, Jim, you haven't said anything today. I was wondering, do you have any comments about what the magnetic field is, or are you, or would you be in the camp where we just don't know how that works? No other comments? Okay. Well, let's see here. So, Dennis, you've raised your flag. Did you have another comment, Dennis? You're still muted there.
Franklin?
Yeah, we can hear you now.
Can you hear me?
We can hear you.
Okay. In any logical theory, there has to be axioms and undefined terms. You can't explain everything. An undefined term, for example, in Euclidean geometry, is a point is undefined, a line is undefined, and a plane is undefined. Although you might define plane in terms of a line, of lines and so on. But the point is, there has to be some things that are not explained in the theory. They're undefined terms. Like in my theory, charge is undefined. Bill has the definition of charge, but he has solitons and things like that. And if you go back farther enough in his theory, he just has undefined terms, which everyone sort of knows what they mean, but they're not defined. Does this make sense?
Well, that's certainly the case. I mean, a lot of dissident theories, if you dig down into them, eventually will come up with like these assumptions and postulates that typically they'll postulate the existence of some particle or something.
undefined terms, like charge in my theory is undefined, and mass in some theories is undefined. I define it as resistance to force. But somewhere, if it's a logical theory, if you go back far enough, you find things that are just undefined, and you have to assume that people know what you mean without a definition.
Now that might be true.
This is true.
Now,
this is true in mainstream theory as well as critical thinking theory.
well, but I think what would be fair is if the thing that you're finally going back to is something which is generally accepted, then that would be okay.
Yes.
So if your theory was based on the existence of like apples and oranges, I think we could all agree that, you know, apples are certain things and oranges are certain things, and they exist.
We know what they mean, but we wouldn't know how to define them necessarily.
But I'm saying that you don't have to be in this hopeless situation where, I mean, some people will say that, yeah, at some point you have to go back to your assumptions and those can't be proven. Right?
No, this is not assumptions. This is undefined term.
Well, would you say, like, if your theory goes back to the existence of electrons, and an electron is an undefined term?
Well, I define electrons in terms of electric and magnetic theory. So electric and magnetic, what is a magnetic field and what is an electrical field is largely undefined, although I define electric field in terms of charge. But charge in my theory is undefined. In Bill's theory, he defines charge in terms of something else. I don't know if solitons are undefined in his theory or not, but if you go back far enough, he will have undefined terms. It's inevitable since he has a logical theory. This is not talking about assumptions. Assumptions are things you assume based on your undefined terms. You talk about charge, for example, and electric and magnetic fields. You have assumptions about them, but in my theory at least, charge is undefined. I just say it acts according to Coulomb's law. It's sort of there are things.
You weren't here last week, I guess. Last week's topic of discussion was, in fact, the electric field and charge.
Yes.
So, and I don't know whether anybody remembered my explanation of what charge is, but I feel that charge is just an electromagnetic wave that's generated by electrons and positrons, and that's how I feel the electric field is actually mediated.
Yeah, in your theory, then, charge would not be an undefined term.
Yeah, charge is actually like a form of light. I mean, it's kind of funny that mainstream kind of defines it that way as well, that they say the photon is the quanta of the electromagnetic field, and if a photon is an electromagnetic wave, then that's what exactly I'm saying. And I'm saying that electrons generate a form of light, which actually, and this is why the electromagnetic field travels exactly the same way as light. You know, electromagnetic field is infinitely distant and travels at the speed of light and has all the same characteristics as an electromagnetic field because basically it is an electromagnetic wave, a form of light being emitted by a charge. The only difference between the negative and the positive charge is that they're just out of phase. And
then in your theory, charge would not be an undefined term. And
charge would not be an undefined term.
But you say a magnetic wave. Well,
but the magnetism, I believe, is different. The magnet, so electric field, I believe, is just like a light bulb. It's like a light that comes off of the thing. But I believe that the magnetic field is, in fact, a very different phenomenon. So since everyone else has had a chance, I'll give you my little spiel on what I think the magnetic
Can I say
field
one thing before you start?
No, I'd like to just go ahead and...
Very brief. I made a mistake earlier. And for a long straight wire, the A field is not lines perpendicular to the wire. It's lines parallel to the wire. Got that back.
The parallel to that. Okay, well, I'm not quite sure I'm convinced about the A field because this is the way I see it, okay? So the way I see it, that the magnetic field has to represent two things. Number one, it has to be a vector, and there has to be a magnitude. So I feel that there must be something physically out there representing that, because I don't believe that if you have space and it's absolutely blank, it has no physical properties, there's no way that it can provide a pointing vector, and no way, of course, it can provide any magnitude. Yeah. So related to my electric theory, I feel that the space is filled with the positrons and electrons, okay? Yeah. So as a substance, a positron-electron pair can represent that vector. You know, the positive end is one and the negative end is the other. So you can point that thing in any direction. So an independent dipole can represent a vector direction, right? So in that way, that kind of medium can represent a vector direction. So what I feel that a magnetic field is if, you know, normally in space, without any magnetic fields present, all those dipoles are kind of like randomly arranged, right? They're just pointing in every which direction, right? But in a magnetic field, I believe they're all pointing in the same direction, right?
Yeah, yeah.
So instead of being random, there's something. So I would say, you know, to answer the question, what is physically different about the space around the current carrying wire? And I would say it's that all of the dipole space around the wire is all generally pointing now in the same direction versus when the current is turned off, then they're just randomly oriented in every which way. And the medium is quite chaotic, so it will immediately revert back to random state as soon as you stop the current. Now the question is, why would the current create this alignment at all? Okay, now that's a little bit tough for me to answer. It's a little bit hard to explain. Why is it when you have all these electrons just flowing in one direction, why does that cause all the dipoles to align in the same direction? Now the analogy I give here is like flags in the wind, right? If you have a bunch of flags and you have wind blowing through it, initially the flags might be randomly oriented, but if you put a strong wind through those flags, they'll all point in the same direction. So like I said, I'm not exactly sure how this works with flowing electric charges. I feel that as the charges flow by, the last thing that they see is like the negative side of the charge. So that causes all of maybe the positive sides of the dipoles to generally point at the last thing they see. And if you have bunches of them, the dipoles can't turn around instantaneously, so maybe that causes them all to stay in alignment. So that's my motivation for why the magnetic field is associated with moving electrons. Electrons are like wind. They comb the field in one direction. So that's my explanation for why magnetic fields are associated with moving charges, right?
Well,
finally, the question is, when you have the electric charge moving perpendicular to, you know, the stream of electrons, or the river, the stream of electrons is like a river, okay? And that's like a wind that's lining all these dipoles up. And then you have this electron, which is moving in perpendicular to that flow. So the question is, why does it flow like with the direction of in the direction of the current? And the way that that works is that if you think of your dipoles that are all aligned, so you'd have all the pluses and the minuses, and the pluses and minuses would be lined up. That if you then shot a charge through these dipoles, like if this was an electron and you would see the positive end of the dipole on one side of it and a negative charge on the other, then you would think just by Coulomb force, the negatives would repel and would be attracted to the positive side, and you'd see the electron deflect. So all you have to do to get an electron to deflect is have it go through a dipole pair, right? It will deflect. And the thing is, if you've got a space which has all these dipoles kind of arranged asymmetrically in the same way, then you would, as long as the charge is moving, then it's going to be deflected by that, just by that alignment, right? So I would say the motivating factor here is that the magnetic force turns out to be actually just electrostatic force fundamentally. That you've got charge against charge being deflected. In fact, I think that's one of my little videos here where I try and demonstrate that. Let's see, do I still have my YouTube? I still have my YouTube up here. Can you guys still see the screen?
Yes.
Okay, so that was one of my magnetic video experiments. So let's see, where is my, okay, here's my experiment showing deflections of electrons, how this would kind of work. Now I'm kind of cheating because I'm demonstrating how the magnetic field works using, I don't know, magnets. But what I'm going to do is I've got a magnet here, and one of them is facing the North Pole, another is facing the South Pole, and I'm going to roll a ring magnet through them so that the magnet is only going to be attracted to one side and to be repelled by the other. And what happens is that when you see the magnet go through, it physically gets deflected towards one side. And that is exactly the source of the force, that it's actually fundamentally electrostatic.
So let's try this.
So I'm going to roll the magnet, and you can see it is preferentially deflected towards one side because it's attracted towards one and repelled by the other, which is exactly what you would see with a charge going between two dipoles. But I think that was just kind of a cute experiment as well. And I also...
Well, Franklin, I think you have a good idea there. A nice way to visualize.
Now, another little challenge that I had here, this is the other magnetic experiment that I did, is that my brother didn't believe that just a coil of wire could produce magnetic effects.
Traction is actually
and so I just have a permanent magnet and just a loop of wire, and then when you energize just the loop of wire, you can see that that actually creates the attractive magnetic effect all by itself. So there's nothing fancy about the loop of wire. There's no magnet present.
And I hook this up using my 101 the flow through these wires.
Now let's get to the actual experiment here.
Is that the electrons will deflect towards the magnet, just like they would say in a TV set.
And I'm showing this because I believe that the actual magnetic force is caused by the deflection of the electrons. So I mean, I explained why the electrons would deflect, but why does the attraction between magnets occur? It's because the electrons flowing through that wire are actually being deflected towards the magnet, and that is what causes the force that we perceive in a magnet.
There's no attraction, only when I depress the key.
So I guess that would be like the final bit of my explanation for when you hold two permanent magnets each other, you can feel that attractive force. And the question is, what are you feeling there? And what you're feeling is that all these electrons are being deflected towards the other magnet. And because the electrons can't escape the physical magnet, they drag the whole physical bulk of the magnet with them. So what you're feeling is the orchestrated effect of like billions of electrons trying to be deflected towards the other electron, and literally pushing the shell of the magnet towards the other magnet, right? So it's not really an internal force like an electric force kind of thing, but it's literally as if there are like a million buzzing bees inside the magnet, and they all suddenly decide to go fly towards the other magnet, and they push their cage with them.
Well, Franklin,
So actually,
I mentioned my explanation of Crane-Monstein effect in terms of the A field. And as I go through that derivation, I use much the same idea. Dipoles are either lined up or they're not. In permanent magnets, like the one in the Crane-Monstein effect, they are lined up. In fact, it's a supermagnet, niobium, fair iron, and something else, and nickel, I think. And that's the way I do look at it. Is in a permanent magnet, the free electrons which would ordinarily be free, all are lined up, and that explains then why when you rotate it about its axis of symmetry, either increases in strength or decreases. I urge you to take a look at that. It's dipole gas is in the title. It's in my in ResearchGate and also on academia.edu. Or I could send you a copy if you want.
yeah, I think, like I said, the dipole, I think, idea is very powerful.
Yeah.
And also explains things like why is it that deflection goes in opposite directions when you reverse the charge, because that's another thing you kind of have to deal with.
Yeah.
That if you think, I mean, one common thing, like I said, is people think that the magnetic field is caused by an actual rotation of some kind of fluid. But the problems with that is that apparently the fluid has to reverse directions if you use positrons instead of electrons, and that can't happen. No. And the other problem is if the charge is just stationary, it doesn't move. I mean, think if it was a fluid moving around the magnet, then all you'd have to do is just put the charge there, stationary, and then it would immediately get pushed. We don't see that. Zero forces are generated on the charge if it's not moving.
Yeah.
And the reason I would explain that is because the charge actually has to cut through these dipoles in order to have any force exerted on them. So if the charge is not moving, then we would expect no force would be exerted. But also, I spent some time, I spent like a month making this particular video about how do magnets attract. And hey, look at that. It's got 18,000 views now. That's a lot more than it was before. But, you know, I'm trying to motivate what is actually going on. And I basically explained that the CRT kind of deflection is really the key to the magnetic force. And that what I have here is my little demonstration. Like I said, you got two bird cages here, and if the birds are attracted to the bird feeder, they'll physically drag the cages with them, right? So, and this is the basic force of attraction. And then you have a deadly kitty cat there, then they'll fly away. So that's how I basically explain how that works. So that's my tour of how I think the magnetic field works. So in a world where there aren't a lot of explanations for how this works, I mean, we've heard like a couple different explanations. It's like the mainstream is going to say it has something to do with relativity. Bill may say that it's just a fundamental force. That's just part of the way things work. It may be that maybe you have a theory of what space is made out of, but maybe not necessarily know exactly what that space is doing. Like that, you know, even a lot of dissidents really don't have really strong opinions on how this whole magnetic field thing works. I mean, I'm probably one of the few people who even have a strong opinion on how the magnetic field physically works, and perhaps even how the electric field works. So, I mean, I don't buy that the magnetic field is in any way fundamental. A magnetic field is a very complicated composite force.
Yeah.
And to say that that is fundamental, I think, is a mistake, because it's a very complicated force. You've got all this B cross B thing that you have to figure out, and you know, there's a couple things that, and I'm not exactly sure whether even my theory really works. Probably one of the bigger objections is that just electrostatic force itself would also cause this kind of dipole alignments. So in some ways we should be able to, I don't know, but we don't think that magnetic fields are generated, say, between the poles of a capacitor, right? But between the poles of a capacitor, definitely those dipoles would have to be aligned, and if we shot a charge between them, they would definitely deflect. But we're thinking because of the asymmetric charges, right? And not because the alignment is, not because dipoles are aligned. So it could be that the magnetic field could be mediated by some other thing. And the other problem is that still can't quite explain why is it the moving electrons cause the field to be combed. I'm pretty convinced that that's what happens, that there's some field out there and the electrons cause that field to physically point in one direction, and that it's the electrons reacting to the charges in that alignment that cause the actual deflection. I'm pretty sure that is generally the case, but not quite sure. Neither am I a huge mathematician. So when I look at like the works of William Cooper and I see all the symbols and the cross products and stuff like that, I tend to just get confused, honestly. That's not an area of my expertise. I'm more of a physical modelist. So I'm hoping that maybe one of those math guys would be able to take a look at what I'm doing and then, you know, do the math. But I generally think you can't do that. But so we've come to the end of our 2 hours here discussing the magnetic field, and we've had some discussions about, you know, how the force works, what's the Lorentz Force Law, what's the B field, what's the A field, what's curl, and you know, how people variously try to explain how this mystery of why charges deflect in the magnetic field. And so we've discussed some possible answers. If you're interested in my theory, then like I said, you just go on YouTube, search for my name. You can see those videos that I was showing. I've got about my experiments about the magnetic field, and do watch my video on how do magnets attract, because I spent like a month on it, and for months only like 40 people looked at it, so it was very disappointing. So I'm surprised to see 18,000 viewers on that video. Someone must have posted it somewhere. So, but that will do it for this week. And like I said, next week, I would invite you to go and join our CNPS conference, where we'll be broadcasting live from the University of Washington between the hours of 9 and 4 o'clock or so, from Wednesday until Saturday. So if you're not able to make it, not an excuse, because we've gone through and implemented quite a bit of very sophisticated technology to bring you this live stream. I believe you'll be able to ask questions to the presenter, just like the chat. All right, so that will do it for this week.